practices. Okay, so this is the very first topic one, and if you go on to, maybe I didn't post it, but I'm pretty sure I did. Yeah, I'm like 90% sure I did, 100%. On the Google Classroom, under the thing that said like Chem review, there is a list of all these things. I just took these out of that list and put them on here, and then I'm gonna write on it, explain that sort of stuff. All right. So the very first thing in this class that we had to go over was about WHMIS. So the different hazards, WHMIS symbols. I hope it's pretty straightforward for you as far as WHMIS. You guys, some of you didn't even do WHMIS. Do you remember there's a safety thing on the Google Classroom. You're supposed to do that. I didn't put that in your marks. I will. So if you haven't done that, it's something you need to get done because it is a marked assignment. But you've probably done WHMIS in the past, regardless, or I hope you have. So these are the different symbols, and it's literally just, can you figure out what the symbol means? So like, I'm not expecting you to memorize these or anything, but you're going to be able to look it up. So like if you see this symbol, you know it's a WHMIS symbol, and that means compressed gas. Some of these you should already know. I hope you know that this fire symbol means it's flammable, right? I hope that's going to be on that's hopefully a common sense thing. Oxidizing, so oxidizing means that if it's got a lot of oxygen and it's open to the air, I guess is what it means, then it can burst into flames. So certain chemicals that if you just open the container and the air fills it, it can catch on fire. So that's what an oxidizer is. We have some of them in this science storage. So it's really important that we put those into a flammable cabinet. Explosion hazard, so something's going to explode. That's a symbol for explosion. Harmful or fatal, poison. You know the skull and crossbones, hopefully. This one, you might see out in public, biohazardous. It's on like needle containers and stuff in the bathrooms. They have needle containers in men's bathrooms. You know, like on the wall, they might have like this like yellow container, and you put like a needle in it. No? Yeah? Okay. I was like, it's women are the only ones that use needles.
I just thought you meant here, but
No, we don't have them in the school, but that's what you would put needles in, you would have that symbol on. So if you take note of it the next time you're in some sort of public washroom that has that, it's not like this is just because it has blood on it, right? The blood would be in the needle if someone's giving themselves a needle. Most of these biohazardous needle things are going to be for people with diabetes because they're going to have to give themselves insulin, and then they would put that used needle in one of these containers, and then they dispose of them properly. You don't just throw a needle on the ground for someone else to stab himself with and then get your blood inside of them. That's how you get like bloodborne diseases like AIDS and HIV. And sharing needles, like if you're doing recreational needle drugs, that's how you get, AIDS and HIV and hepatitis. All of those things we don't want. So really important that we put our any sort of biohazardous waste. If you had an organ or something removed from you in surgery, they would use this symbol on it too. Corrosive. This is something that can burn your skin. So you put it on your skin and you start to feel like you're drying out, your skin peeling off. That's corrosive. This one is a health hazard, so in some way maybe ingesting it or breathing it in is going to be hazardous. This exclamation mark is harmful, and then this last one is harmful to the environment. It has like a little tree and a fish on it. Okay, so those are the different WHMIS symbols. Again, you just have to be like, I'll probably ask you like, what does this WHMIS symbol stand for? Okay, really basic. I'll probably ask you like 1 or 2 questions because I hope this is all review. In the past, you guys may have had different symbols. They actually changed the symbols in 2015. So these are new symbols from 2015. But before that, there was some different symbols, and that may be why some of these might look new to you. Because some teachers will still use the old symbol system. Bohr diagrams. What are those?
Circle.
They're circles, yeah,
It is.
around the elements, right? Do what? Yes. So symbols around the elements, electrons, yeah. All right, so the best way to describe this is let's just do one. So pick an element between 1 and 20.
Magnesium.
Magnesium is number 12. The symbol for magnesium is Mg. I'm actually going to write this to the side in case you want to do another one. Mg, so we would always write down the symbol's name, and then we figure out how many electrons are in magnesium. How many are there? You need the periodic table, super important. This is your chemistry Bible or whatever. This is magnesium Mg. It's number 12 in the table, which means that it has 12 electrons. So whatever the number is in the table, that's how many electrons it has. So I'm going to write down that it has 12 electrons. I just wrote it right on the side, E with a little line on its electrons. And then we need to figure out how many circles are going to go around it. So if we look at the periodic table, and we go from top down to where magnesium is, we count 1, 2, 3. From hydrogen, lithium to sodium. So it's in the third period on the table. So it requires 3 circles. So we draw those circles around it. Okay? Okay so far? Now we need to put those 12 electrons in. Where do we put them?
2 in the first column.
2 in the first? Why 2?
Because there's only 2 things in the first row.
Yeah, so our circles, how many elements or electrons are we put into it, tells us in the rows of the periodic table or the groups. So if we go to the very first period, hydrogen and helium are the only ones in that period. So that is all that we can put in that row, or in that circle, valence shell. Second one, how many can we put?
8.
8. So if we go to where lithium is in the periodic table, we count across to neon. There's 8 elements there, which means we can put 8 electrons in our second circle. 1, 2, 3, 4, 5, 6, 7. All right. So now we've got 2 in the first, 8 in the second. We've used up how many? 10. 2 and 8 is 10. We need to put in 12, so how many go in the last circle? 2. So we put in 2. I like to keep track sometimes. 2 in the first one would give us 10. And then we put 8 in the second one, which gives us 2. And then the last circle will have 2. Does it matter where we put them?
No.
No, it doesn't matter because this is representing something that's swirling around in a circle. We don't actually know where they are at any time. That's how you do a Bohr diagram. Want to do one more?
I guess.
Let's do boron.
And
What's the symbol for boron? How many circles do we put around it?
2.
Are you sure?
Positive.
Yes, positive. So we go from hydrogen down to the second row, period, sorry, it is in freon, lithium, beryllium, and boron. So that is the third one in on the second row. Second row means we put 2 circles. One, oops. Hard. Perfect. So now we've got those 2 circles. So how many electrons are in boron?
5.
5. How do we know that?
But
It's the atomic number. The number on the periodic table is 5 for boron. So we put 5 in. 5 electrons. How many do you put in the first circle?
2.
Always 2. And then we only have 5, so 5 minus 2 gives us 3. So we put 3 in the final circle. That circle, or that outer shell, circle is called the valence shell. And that valence shell is the ones that are, the electrons that are there that could bind to other ones. Okay? Those are the ones that are free moving, and they, remember, everyone wants to have 8 in their outer shell. They want to be cool like the noble gases, the heliums, the neons, the argons. So to be cool like them, they need to bind together, and that'll become clear in a second. Lewis structures. What are those?
Dots.
Dots. Elements and dots. What's and a symbol? Okay, what? Name one. Name an element.
Neon.
Neon. So the symbol for neon is Ne. And then we put dots around it. There's no circles involved. There's just dots. How many dots do we put? From the left to the right. Yes. So we don't put 10. 10 is the amount of electrons. We're only putting the ones that are in the outside circle, or the valence shell. So for neon, we just, or for all of them, we need to count left to right. So we start at lithium. 1, 2 beryllium, 3 boron, 4 carbon, 5 nitrogen, 6 oxygen, 7 fluorine, and 8 is neon. So this means we have 8 dots that we need to put around. The dots are electrons. So let's do that. Where do we start?
Top.
Top. Where do you go then?
1, 2.
Is that good? Yeah. And then go where?
Top again.
Top again?
Clockwise.
Clockwise, always pairing. Yeah. Perfect. So that's neon's Lewis structure. These are much more important when we're talking about everything from chemistry now on, from this point, just because Bohr diagrams, we don't really care about all the other electrons, we just care about that outside shell. Let's do one more. Let's do aluminum. How many dots do we put in aluminum?
3.
3. So we start on the left and work our way to the right. Sodium 1, magnesium 2, and aluminum is 3. We don't count any of those transition metals. So all those titaniums, chromiums, manganese, all those, we don't count. We just count the ones that are in our row. So if we're doing the dots for this, we always start at the top and work our way clockwise. So this would be our Lewis structure for aluminum. Okay? Is that one? Ionic versus molecular. All right, so this is talking about bonds, and we need to distinguish what each of these bonds are. So what is an ionic bond versus a molecular? This is something we do in science 10 to death. To death. I literally almost died how much time we did this chemistry stuff. Like at least half of the class. So what is an ionic bond? There's a key word inside of ionic.
Two bonds connect.
Yeah.
Two,
Two elements connect, but what kind of elements?
a metal and a gas.
Yeah. So ionic always have a metal and a non-metal. And the key thing here is that it has to do with charges. Metals are positively charged, non-metals are negative. So that's the positives or opposites attract sort of thing. We've got the positives and negatives bonding together. What's a molecular bond?
Non-metal and a non-metal.
A non-metal and a non-metal?
Yep.
Yeah, so does it have anything to do with charges? No. So molecular bonds, no charges. So two non-metals, no charges, molecular bond. Okay. Something to really note is if we were to draw Lewis structures of these ones, they give electrons. And molecular bonds, they share. I can do an example of that on the side, maybe. So an ionic bond, let's do my favorite one, NaCl. So Na has one dot on its Lewis structure. Chlorine has 7. Okay, so to be happy, they can be happy together. This sodium will actually give chlorine their ion or their electron. When they give away an electron, they become positive, right? More positive, and that's why sodium has a +1 charge. So this is a give. Giving. I'm sorry that my writing is so bad on here. For a molecular bond, let's do H2O. Hydrogens each have 1 dot. Oxygen has 6. So instead of, they do share electrons instead of giving them away. So I guess I should draw these in the proper spot. So next to each other, this looks really stupid and not very good. But these are shared. So these ones share, and that's what connects them. These are a weaker bond. We can break bonds between hydrogen and oxygen in water, but you need a whole lot of energy to break these. These are strong. Okay? If you wanted to have salt, sodium chloride on the table, and somehow to be able to get the sodium away from the chloride, like good luck. You're going to need a lot of energy, where not that much energy can be used to break the bonds between water. Okay? So, refresher here, ionic, metal and non-metal, they have charges, they they give away their electrons, and they're a strong bond. Molecular, they are two nonmetals, they don't have charges, they share their electrons, and they're weaker. Okay? So that's the whole thing about bonds there. Try and electrolytes. Electrolytes are what? Where can we get electrolytes? Do you have any idea? Do we eat electrolytes in our life? Yeah, we do. Where do we get them, maybe?
Water.
Mm-hmm. Yep. Water. So we think of water as being just H2O, but the water that we drink actually has other things dissolved in it. Like you see on this thing, it says spring water. Spring water has different things dissolved, and there's actually on this one a chart that says like what's in there. That's not actually the water that's in there, but there is elements or minerals dissolved, and those are electrolytes. So I'm gonna say they're minerals. So the minerals are ions in water. So all the electrolytes are sort of different ions. So there could be magnesium and sodium and potassium and chloride all in your water. And that's a good thing because we need those in our body. You know, like if you are doing really vigorous activity and you're sweating a lot, you might need a lot more water. But you know, some people drink something like Gatorade. Gatorade's an electrolyte drink. It brings back your salts. So it's really a type of salt. When we talked about electrolytes in this class, I think all they wanted you to talk about, maybe I'm wrong. I think maybe we just needed to know what they were. I'm getting mixed up between Science 20 and Science 30. I was going to tell you something else, but I think that's a Science 30 thing. So just knowing minerals or ions in water. So some different examples of it might be sodium and magnesium and chloride and fluoride. I don't know. Calcium. So those would be some electrolytes. They're basically dissolved in your water. The water that we use in the science lab, distilled water that has none of these minerals in it. If you were to drink it, it would start to leach the minerals out of your body. Okay, so we need these. We don't want to drink pure water. We need to drink it with ions in it so that they can add to our body as opposed to pull stuff out of our body. That drink eagle has been called quite a few times. Solute versus solvent. So what is that? What's a solute versus a solvent?
Solute is water, or is the liquid you're going to use to make something.
Someone above us.
Yeah.
What the heck? Someone's on the roof, obviously.
Probably that drink.
Oh my god, can you imagine? Drinks just on top of the school.
Water
Water and what?
and
Iced tea? Yeah. So which one's which?
water would be the solid, would be the solid. Is
So a solvent is always the thing that's dissolving the stuff. So solvent is normally the water.
oh, that's rude.
What? That's
Nothing.
and the solute would be the smaller amount. That's really all you need to know about that. Concentration and dilution. What's concentrated? What does it mean to be concentrated?
It's the same. 100%.
100%. Yeah. It's concentrated, so it has like 100% of something. So you're using a certain way of describing.
100% water.
Yeah. So concentrated means the amount of solute is high, I guess. If you're talking about something that's concentrated. So the solute would be if you had water and food coloring. The more food coloring you put in, the more concentrated it is, right? Diluted. So what does it mean to be diluted?
Less.
Yeah. Less solute. So if you had something that was really dark versus really light, you'd be like, this is the dark one, it's the concentrated, the lighter one is the diluted. Okay? Really all we need there. And then this brings us to the way we calculate concentration. So I put this chart here. This is in your notes. These are the different ways that we can calculate it. We're going to do one example on the next slide. But just to go over these, so there's 3 ways we can calculate concentration. Landon, you said one was percentage, which is definitely one. So volume of a solute divided by the volume of a solvent times 100. So the volume of the thing that's smaller divided by the volume of the amount of water we have times 100 will give us the percent that is in there of that solute. The next one, parts per million. So this is what we would use when we're talking about pollution. So a mass of our solute divided by our mass of our solvent times 10 to the 6 will give us a parts per million. And you can always look at this when you're doing your tests so that you have your formulas there. And then the last one is your molecular concentration. So this is the one that we use the most. And the formula that we normally use for this is, are you okay, Kai? C is equal to N over V. So C is the concentration is equal to our N, which is our moles, divided by our volume. All right, so let's go to the next one and try this example. So when I'm reading a question, first thing I always do is write down the pieces of information that they give us. I'm just going to get my highlighter so we can highlight that. So a student mixes 27 milliliters of hydrogen peroxide with enough water to fill a 400 milliliter container. There's a word missing there, with, but anyway, that's my bad. So they have some hydrogen peroxide and they're going to mix it with water. The question asks, what is the percent volume concentration of the solution? So we're looking at a percent concentration. If you look back at this little chart, it's going to tell you these are the 3 ways we can figure out concentration. The question said percent volume, so this is the formula we're going to use. Okay? So it's the volume of the solute divided by the volume of the solvent times 100. So I'm going to write that formula here. The volume of the solute divided by the volume solvent times 100. Okay. So for us, we need to plug in the pieces of information from the question that it gives us. So I'm just going to highlight these 2 because that's our 2 pieces of information. So So which one of those is our solute and which one is our solvent?
Solute is the 270.
The 27. Oops. Yeah, it's 27.0. Okay, so that's our solute, and then our solvent is always going to be water, almost always. All right, so to plug it into this formula, we just need to write our volume of our solute divided by our volume of our solvent. So our volume of our solute is 27, and our volume of our solvent is 400. What we talked about before is that you always need to change your stuff into liters, but you don't have to do that here, just because as long as they're the same. So see how this one's, they're both in milliliters? When you divide them together, they will still be in milliliters, so it's fine. The only time you need to change it into liters is when you're dealing with moles. So whenever you have moles in the question, you need it to be in liters, okay? This would not change it. If you change that into liters, you would still get the same answer. So, not important. So we go 27 divided by 400 times 100. And then whatever the answer is to that. Does anyone calculate it? What's the calculator? 27 divided by 400. It's going to be a very small percent. Oh, percent. Okay. %. So that is how much concentration of hydrogen peroxide in the water. Okay? When I looked at you, I thought you were saying something weird. I forgot you had to times it by 100. I was like, it shouldn't be over 1. But so if we didn't times it by 100, it would be like 0.0675.
Yep.
Yeah. That's why I thought that was a wrong answer. Alright, so that's how you would do that type of question. I'm not going to do any more of those, but you can look at your original notes. We do examples on that, on parts per million and molar concentration. But when you're doing your test, just look at this. This little chart will tell you what you need. Okay? Yep. Okay. We've got our calculation of dilution, so I'm going to go over this one right now, and I'll give you guys a break from this, because that'll be like the first section of chemistry, and then we'll do the second after. Give you a little bit of time. So dilutions. To do dilutions, there's a formula we always use, and it is, does anyone know? I can tell you. This is reviewing you, I know you guys are really awake.
Yep.
Concentrations are dilutions. How do we do a dilution question? What's the formula we use? This formula is going to be used again when you do Science 30. I think, I don't know if you looked at Science 10, but it's going to come up a lot. It's C1 or CIVI is equal to CF Fiat. So CI is the initial concentration, VI is the initial volume, is equal to your final concentration times your final volume. Is this ringing a bell? You've seen it? Okay, good. Let's try a question out. So the question here says, what would Before I read the question, I'm going to make a little table on the side. Because I like to write down the pieces of information I need to figure out. We should have 4 pieces of information. The question should tell you 3 of them so that we can solve for the missing one. So it says, what would the final concentration be? The question right away is telling me that we're looking for a final concentration. I always like to put a question mark. So that's probably the one that we are dealing with. That's the one that they're asking us to find out. We should have all the other pieces. What would the final concentration be of 4.5 liters of 1.7 moles per liter solution of acid we're diluting? That's what we start with. So our 4.5 is our starting amount of volume. So I'm going to write that in initial volume. It's a 1.7 moles per liter solution of acid. That's a concentration. So I'm going to write it by concentration. So if this was diluted to a final volume of 6,000 milliliters, that's going to be our final volume. Can we go ahead and do our question? We're missing something. I made this question this morning to throw you off. Look at our units. Is everything lining up?
No.
What's wrong?
We have moles, liters.
So is our volumes matching up? No? So we gotta make them the same. What do we gotta change them to?
Liters.
Yeah. Maybe this is meant just to see if you guys would be able to figure it out. And you didn't. So it's 6,000 milliliters. So to put it into liters, we always got to divide by 1,000. So whenever you're changing to liters, you're going to divide by 1,000. I always just move the decimal 3 places. So 1, 2, 3. So that's really 6 liters. Okay. So if you do divide by 1,000, you're going to get 6. Good? Sorry for my 6s. It's always something I need to work on. Okay, so that's our 6 liters. So now when it's all in liters, we can plug it into our formula. So I'm going to rewrite the formula here. CIVI is equal to CFVF. And then we're going to plug in the pieces we got. CI, what's our CI?
It's definitely not 1.7.
1.7 is our CI times our VI.
Definitely
4.5. So we're going to multiply those, and it's going to equal our CF. We don't know what our CF is, so we're just going to write CF. And our VF we know is to be 6. Okay. So what do we got to do now?
Figure out our CF.
Yeah, that's the goal. We want to figure out our CF, so how do we do that? We don't. So we want to find out the final concentration of this solution. We need to isolate CF. So if we're doing this, we want this to be on its own. So that means that we're going to have to bring this guy to this side, right? So to do that, we want to get rid of it on that side. So if it's multiplied on the right-hand side, how do we get rid of multiplication? We always do the opposite. What's the opposite?
Divide.
Divide. So what we do to one side, we gotta do to the other. So we're dividing by 6. 6 divided by 6, it'll get rid of that. So then you're left with CF. You know what, I'm just going to erase this temporarily to get it out of our way. So we're left with CF on the right hand side. And on the left hand side, we're left with 1.7 times 4.5 divided by 6. You gotta calculate that? Did you? So 1.7 times 4.5 divided by 6 is what? 1.275, that's a concentration, so we need to be in moles per liter. Okay? Because this is our final answer, we need to write this in 2 decimal places. So this is actually going to become 1.2. Because it was 1.275, that 5 is 5 or higher, makes us round up to 1.28. Okay. So that's our final concentration. That's how you would do a type of question like that. So it's always going to give you 3 pieces, and you've got to find out one of the pieces. In this case, it was CF. Okay? That is topic 1. We'll take a break from that for your brains.